And now they could be continuous or discrete. Now a stochastic process could be continuous, so it could be something that changes continuously, or a stochastic process could be discrete. It is defined only at a specific instance. So for example, if you assume take stock market as value of a stock as a random process, then in some cases you will find its value specified only at the time when the market closes. So in that case, you can regard that as a discrete process. However, if you are a day trader, how many of you heard about day trading? That is one good way of losing money, so they say. But apparently some people make money, but so in that case, they just sit at their terminal and watch the market go up and down all day because it's continuous. So in that case, it's more a continuous stochastic process. So you will see both types of modeling. In some cases, it makes more sense to use a discrete stochastic process, but a lot of times continuous makes more sense. Okay. Now let me talk about a Markov process. A Markov process is a discrete state. Oh, I keep on using the wrong word there. Discrete state. That means that there are some well-defined, nicely separated states, but continuous time. Process. And now here is what is called the Markov property in the next sentence. Transition probability from state I to some other state, let's call it J, depends only on state I. So it does not matter what has been the previous state. It doesn't matter which previous state you came from. It doesn't matter how long you have been in state I. The only thing that matters is that it is in state I at certain time, and then you can calculate the probability. In other words, the Markov property means that it is memoryless. So the process has no memory. And now, a lot of time when we will do modeling, we want to assume that it has a Markov property. That means it is memoryless, and that makes the analysis much easier. If it has memory, then you have to take memory into account, and that can make your calculation cumbersome. Other tools are available. So even though time to time we will make approximations, and I will state the approximation, but if you want, you can remove the approximation by doing more detailed analysis. You just have to go to the literature and find out how you need to do it in a more detailed way. So Markov process is a discrete, say, continuous time, and there is something very similar which is called a Markov chain. And Markov chain is discrete state and discrete time. Otherwise, it's the same thing. Markov process, Markov chain, they are practically the same thing. And the only difference is that in case of a process, you are doing modeling continuously. In this case, you are doing it at specific instance of time. And a lot of times, for a given process, you can use either this or this. Both of them will work. And the methods are somewhat analogous. They would look different mathematically, but if your approximation is reasonable, then they should give about the same result. Okay, now let me mention about Poisson process. So the Poisson process is a Markov counting process. That means you are doing some counting, and your count is given by number n, which goes up as time goes by, and you start counting at time t equal to 0. You don't start before time t equal to 0. In other words, whenever you start, that is time t equal to 0, then such that nt is equal to, nt is the number of arrivals up to time t. So this is a Markov process, which is often a Poisson process, which is often used for queuing theory. I have Omar, I had a question for you.
Yes.
You submitted your assignment, and I couldn't read your format quite well.
Okay.
So what format did you use?
I used the OpenOffice.
Oh, okay. So you should convert. You should convert it into PDF and then submit.
Do you want me to resubmit it?
Yeah, can you resubmit it so that I can see? So I was able to kind of make out, but it had a lot of this XML stuff which was first in it.
Sure,
So,
I will definitely do that.
So yes, do that, and also, so I think you know how to convert it into PDF.
Yeah, sure.
I think OpenOffice is sort of built in.
Yeah, it's a built-in function.
Okay. Now, actually, now in modern, the newer software is mostly built in.
Even with the Windows, Microsoft Word.
Right. So, okay.
I'll definitely do that.
Okay. So, yeah. So I was mentioning here about the Poisson process, and now here, let us see an example of a Poisson process. So we want to calculate the probability of n arrivals in some time period t. And we have seen an expression for that already as an example of the Poisson distribution. Oh, this seems to be working now, the clock. I guess that somebody must have put in a battery there. So let us analyze a Poisson process. And this is actually a good example of how Markov processes are analyzed. So we will say that a process, or the process is in state I if I arrivals have happened. And let us indicate by p sub I t the probability of being in state I at time t. Okay, so now let us give a model for the process. So let us say we start here. Here is state 0. That means no arrivals have occurred so far. That means we basically start the clock here. We begin and we wait for the first arrival. So here is state 1, and let us assume that the arrival rate is governed by parameter lambda. Another arrival, we go to state 2 and so on. And here is state I, here arrival, and here we go to the next state and so on. So now probability in state I, notice that there is some probability flowing in and there's some probability flowing out. And we can describe this mathematically. So probability of being in state I is changing, and there are two reasons why this is changing. So the rate of change of being in state I is given by two factors. One factor is you have the probability going out, so there's something that you are that is a negative component. So minus lambda multiplied by probability that you are in state I. So this is the rate by which probability is leaving, and the rate by which probability is coming is plus lambda pi minus 1t. And here your I is equal to 0 to n. Well, let me see. I equal to, well, I guess there's no limit to how big it can be. So we have this, okay, so here we have an equation. So you can come up with an equation for P, this is an equation for Pi. We can have an equation for P2. We can similarly have an equation for P1 and so on. And so we have a number of these equations, and we need to solve these set of equations. And it turns out that solving this set of equations is not that hard. And what we will do is first we will solve it for this. That is the easier problem. So we'll solve the equation for this. So once we have solved it for P0, then we can solve it for this. And once we have solved it for P1, we can solve it for P2. Remember, in order to characterize Pi, you need Pi minus 1. So let's start with P0 first, and that is the easier problem. So P0, let us use P0 to indicate probability that the process is in state 0,